Hello, grade 12. So, lesson 2, we're going to be nice and quick because I'm sharing an office with Miss Mitchell and she has other things to do than listen to me speak. So, we're talking today about normals and equations of lines. So, kind of building on our first lesson. A normal, we have already seen this before. Remember, a normal is something that is perpendicular to a plane. Now, a dot product of a normal and a vector is always going to be 0 because they are always perpendicular. So if I were to look for any equation, ax plus by plus c equals 0, I know that my normal is always going to be the inverse of my slope, which will be a comma b. So that's always going to be my normal. But for the most part, you're not going to see it in this form. If you see an equation like this, find the normal to the line. Here I can see, and I'll break it down in the first example, that my slope is 3. So if I have a line 3 over, 3 up, 1 over. That's that nice slope here. In terms of getting something that is perpendicular, I switch my components. So my normal would be 1 over, 1 up, 3 over, and negative. In terms of this line, I'm looking for a normal. Remember, this is my direction vector here. So it's going to be the reverse of my direction vector. Where am I? Maybe do it in 2 steps. Direction vector is -3, 7. Think that's like run and then rise. So my normal will be 7, 3. Okay. So notice that I'm going, in this case, 3 left and 7 up. The reverse of that would be to go 7 to the right and down 3. So notice that this should be a negative there. Those lines will be perpendicular. Something a little bit easier, find the equation of a line with this normal passing through the point -1, 5. So I have my normal, and I can convert that into my direction vector. And I now have a point, so I can write the equation x comma y. Oh, I wanted it in standard form. Of course it did. So start off, you can do your point, -1 plus 4t, and y is 5 plus 3t. Rearrange and set equal. To get my overall equation here. Make sure when you're doing your normal vectors that you ensure that you're switching it. So 3, 4, make sure your sign is changing to 4, -3. So here when you cross multiply, I am left with -3x minus 3 equals 4y minus 20. And remember, in standard form, your a value for x is positive. So I have 0 equals 3x plus 4y minus 17 as our final answer. Okay, so get comfortable converting between normals and direction vectors. On the other page as well, you're taking your normals and you're changing the sign on one of the variables there. So here that would remain a positive on that last page. Okay, second last part of this, find a scalar equation of a line with this normal passing through this point. So converting this into my direction vector, 2, -6 is the easiest way to do that. But remember, you have to reduce 1, -3. Scalar equation that we're looking for is our, it doesn't specify standard form. So for me, I'll set it up with components first and set them equal to get a symmetric form and go from there. So this is -3 plus t, and my y value is -5 plus 2t, sorry, plus 3t here. Isolate to set equal. And cross multiply just to simplify our lives and make everything more beautiful. Three x plus y plus 14. Beautiful. So normals, direction vectors, kind of same thing as we've seen before. So now I am essentially going to summarize what equations of lines in 3D space look like. Although this is a little bit different than what you've seen, but only because there's just an additional z and m component. These are still my parametric equations, and the one in the middle is still my vector equation. Here is your summary page as seen below. Remember, to go from vector to parametric, split up your terms. To go from parametric to symmetric, isolate for t and set equal, and then symmetric to get scalar. Okay, so why I'm bringing this up is that scalar, that made sense before. I could cross multiply and I would isolate to get an equation of the form ax plus by plus c. But now that I have a third term, I actually don't have scalars. Scalar equations only exist for lines in 2 dimensions. Equations of lines in 3 dimensions are either vector, parametric, or symmetric. There are no scalars, so we kind of lose that last part. Here's the 2 examples that we're going to look at. Determine a direction vector passing through the point, blah, blah, blah. AB. So first find my vector AB. Remember, it's B subtract A. -4 minus 2, -6, -12, and 6. So I have my vector AB, and remember I pick a point. It wants a direction vector, so that's the direction vector AB here. I can relabel it, but please ensure that I am, should be square brackets, reducing. So this is -1, -2, and 1. So you can see I factored out a 6. Notice how there are 2 negatives and only 1 positive. It's nicer to reduce it to 1 to -1. So that's the final solution that I'd like to see. What is the equation that passes through these points? So I look at CD. This becomes 1 minus 3, -2, 7, and 2. Can't reduce it. It wants the overall vector equation, so I'll pick this point here. Doesn't matter though. 3, -4, 6, plus t. Beautiful. Break it up into parametric and symmetric equations. So my x is 3 minus 2t, and z 6 plus 2t. And then for my symmetric, isolate for t in all of them and set equal x minus 3 all over -2, y plus 4 all over 7, z minus 6 all over 2. And you're done. 2 more small points, a little bit harder. Does this point lie on the line? Well, if it does, my symmetric equation above should be equal. So there are 2 ways to do this. Plug in and solve for t or sub to the symmetric. I like the second version better. I think it's a little bit easier. So negative 3 minus 3 all over negative 2 is equal to 17 plus 4 all over 7, 12 minus 6 all over 2. Negative 6 divided by negative 2, positive 3, 21 divided by 7. Hey, look how nice this is working out. Therefore, yes, it's on the line because 3 equals 3, which equals 3. The last part here, write a vector equation for this line. This is always a final exam question. And it looks trickier than it is because it gives you x minus 1 equals y, which equals negative z. Keep in mind that this is a symmetric equation. All of these terms equal t. So x minus 1 equals t. Break it up into the two parts. Negative z equals t. Now, to get x by itself, and now I can go right into the vector equation where I have x, y, z equals the point. Well, the point is 1, 0, 0, and this is a 1, 1, negative 1. So notice the reasoning behind these zeros is because there's no actual numbers associated here. And that is my beautiful vector equation. You have the rest of class now to work on these practice problems as well as an additional review sheet, which is posted. All right, thanks.